arcs and central angles, those are both new terms for you. So we're going to have several new terms today, as well as some theorems or ways to solve problems. Our first new term is central angle. So a central angle is an angle with its vertex at the center. So we're going to have a circle, and we're going to make an angle with its vertex at the center of the circle, and that would be a central angle. So central angle, vertex at center. A minor arc. What does the word minor usually mean?
Small.
Small. So the minor arc is the small arc across from a central angle. A minor arc is a small arc that would be across from a central angle. Minor meaning small, meaning it must be less than half of the circle. Okay? Less than half of the circle for a minor arc. So then the other side of that would be a major arc. Major usually means large. So a major arc must be more than half of the circle. And so a major arc would be the rest of this circle. So when we talk about an arc, we are going from point to point along the edge of a circle. When we name arcs, I'm going to put some letters in here. If I name a minor arc, I'm going to do so with 2 letters. And put a little hat on it, a little curved section, like our segment symbol, but curved, meaning that that is an arc. Okay? When we name a minor arc, we're going to use 2 letters and put a little curved section of an arc above it. A major arc will be named with 3 letters. So when you see an arc named with 2 letters, that means get there the quickest way. Go from A to B the shortest way possible along the edge of the circle. But if I wanted to talk about the major arc, the other half of the circle, I have to give you a direction to start at A, go through C, and around to B. Major arcs will be named with 3 letters. Okay, the center letter giving you the direction to go. So if you only see 2 letters, that means get there the quickest way possible. If you're supposed to take a longer route, there will be 3 letters that gives you a letter you need to pass through. So I start at A, pass through C, and go around to B. A semicircle is an arc with its endpoints on the diameter. What is the diameter? Line goes through the center from edge to edge on the circle. So it's a chord that goes through the center. So a semicircle, if it has its endpoints on the diameter, will be half of the circle. Okay? Minor is less than half of the circle. Major is more than half of the circle. If it is exactly half of the circle, that is a semicircle. The measure of a minor arc, the size of a minor arc, it says is equal to the central angle. So we have our central angle. We'll say that that is 80. The measure of the arc would also be degrees. Arcs will be measured in degrees. Okay, arcs will be measured in degrees. And an arc is equal to the angle that cuts off that arc, equal to the central angle that cuts it off. So that minor arc is equal to 80. If I wanted to know how large the major arc was, the rest of the circle, well, how big is the circle? 360. So if I wanted to know how big the rest of that arc was, I would take 360 minus 80, and I would get 280. Okay. So a minor arc is equal to the central angle that cuts it off. The major arc is the rest of the circle. So 360 minus the minor arc. A semicircle we said was half of a circle. How big is half of a circle? 180. So So a semicircle measures 180. Adjacent arcs are arcs in a circle that have exactly 1 point in common. So if I have A, B, and C here, the arcs AB and BC would be adjacent arcs. They share that 1 point in common. They don't overlap at all, and they meet up next to each other. We have an arc addition postulate, which is a lot like our segment addition postulate from a long time ago. What did the segment addition postulate say?
That AB plus BC equals AC.
Yeah, so if we had two segments that were in a line with one another, we could do AB plus BC, and that would equal the whole segment length of AC. We can do the same thing with arcs according to our arc addition postulate. If I have two arcs, I can take the measure of one arc and add it up to the measure of the arc that's next to it and get the measure of the whole arc. Congruent arcs would have the same measure. We can have congruent arcs be in different circles as long as the circles are congruent. What does it mean for two circles to be congruent? That was a term from our first lesson. What's the same about them? The radius, the size of the circle, which is determined by the radius, is the same. So I have two circles that have the same radius and the same degree measure for an arc, then those arcs are congruent. And Theorem 9.3 says if we're in the same circle or in two congruent circles, the minor arcs are congruent if and only if, the only way this can happen is if those central angles are congruent. And the reason is because an arc size is determined by the central angle. So if those angles are congruent, then the arcs would be congruent. If not, then they won't. It's the only way that two arcs can be congruent is if those central angles are congruent. Questions on any of our new terms or theorems? Let's look at some examples. In this picture, I have some central angles measured out, and we are asked for some arc measurements. How big is arc AB? 50. How do you figure? So it's the same as a central angle. The measure of a minor arc is the same as the central angle that cuts it off. How big is the arc from A to C? How do we figure 130? We add up the two arcs that are next to each other. So AB would be 50, as we said in the last one. BC would need to be 80, matching its central angle. And our arc addition postulate says that we can add together arcs that are next to each other. So we can add up 50 and 80 and get 130. ABD, named with 3 letters, gives us a direction to go. I start at A, pass through B, and go around to D. How big would that be? 180, adding up all of those angles together. That means that ABD is a what? Semicircle. 180 degrees is half of a circle. So ABD is a semicircle. BAD, starting at B, passing through A, down to D, we'll measure that. 230, how do we figure? If one half of the circle is 180, the other half must be 180 as well. And starting at B, going to A we get 50, all the way around to D, 50 and 180 gives us 230. CDA, starting at C, going around through D to point A, gives us 230 again. It's the same thing, just on the other side. We have a 50 and a 180 again. CDB, starting at C, going through D around to B, gives us 280. How do you figure? We can either do it by addition, adding up the portions that we're getting, or we could do it by subtraction and say it's the whole circle except for that 80-degree portion. So 360 minus 80. Questions? In this one, I gave you some measurements of arcs. Arc GF is 60, arc FE is 50, Q is at the center, and H is just floating out there. How big is angle GQF? 60. How do we figure? The central angle should be equivalent to the arc. Okay. Central angle is the same size as the arc. EQF. EQF, 50. Again, central angle is equal to arc. So we know this angle is 60, this angle is 50 because that's what their arcs measure. GQE. 110. We could think about either our angle addition postulate here, adding up the two angles we just calculated, or the arc addition postulate, adding up the two arcs and thinking about that full angle at the center then. Arc GE. (110), same as the last one. Arc GE is the arc that is cut off by angle GQE. So those would be equivalent. Arc GHE tells us to start at G but pass through H heading around to E. Would be how much? 250. How do you figure? Subtracting the 110 from the 360. It's the major arc that goes with the minor arc of the last question. It's the rest of the circle. So a circle is 360 minus the last answer gives us 250. EHF, starting at E, through H around to F. 310, how do you figure? Whole circle minus the 50 that we're not covering. Questions? Your homework is from section 9.3, and I need to give you a heads up on one of the questions. On question number 10, you will be given a circle with a diameter and an angle drawn in. An extra line connecting. We will be asked to find angle 1, which is labeled in the picture here, and in the book, put angle 2 just kind of floating in a space that's pretty non-distinct. It's kind of hard to tell what they meant that angle 2 to be. Angle 2 is supposed to be that angle. So we want to make sure we're calculating the correct angle there. So what you will be given in each question is an arc value here, let's say of 60, and asked to calculate the size of those two angles. How big is angle 1? 60, because a central angle should equal the arc. We do not have a name for angle 2 or a special rule about angle 2 from today, so now we need to do some calculations. So what could I do to try to work my way over to figuring out what angle 2 is? Okay, so right next to it I can do 180 minus that 60, and I know that has to be 120. How can I work my way back to angle 2? What do I know about that triangle? How do you know it's isosceles? The radii have to be the same length. We have two radii there, and all radii in a circle are the same length. So we have two radii, make this into an isosceles triangle. In an isosceles triangle, two sides are the same, but what else? Two angles are the same. So these two angles have to be the same. And if all angles of a triangle add up to 180, how big are those angles? 30 each. Okay? So in number 10, there will be a chart, and you'll work through a few examples with different values such as this. Then in the last column of that chart, they give you just a variable. By that point, you should be able to determine a pattern in your answers between the relationship of angle 1 and angle 2. Number 11 builds on that idea of that pattern.